Okay, so let's start with my talk. It will be a journey through ESIL, understanding code emulation with r2con. First of all, who am I? My name is Arnau Gàmez. I'm a student of Maths and Computer Science at the University of Barcelona. I'm also the president of Hacking Lliure. You might have seen some stickers around there. This is a non-profit hacking association that I run with some friends from the faculty, and not only the faculty nowadays. And we do some crazy and funny stuff. And I'm also a quite long time collaborator of R2 Congress, and especially managing administrative staff. I'm the guy who manages all of your tickets, so be kind with me. And I'm passionate about r2, and I participate in the community as much as I can. So the motivation for this talk is, first of all, I wanted to force myself to understand the basics of how ESIL worked and what it does, why it was implemented and in the way, and how to do basic stuff with it. And another important point is that I already gave a very similar talk to this, but it wasn't recorded or uploaded, and I received quite a good feedback, especially from people not really introduced in reversing or code emulation, or they didn't know exactly what was ESIL and how to use it, and they asked me to do it again for it to be recorded and uploaded. So this will be the case, hopefully, and also show some very simple use cases. As you can see, this will be a quite basic talk. So if you are a intermediate to advanced user of r2, probably you will know most of it, but I will center not that much on showing ESIL configurations and many things about using it for a bunch of stuff, but how it works and what is behind it, and then we'll see some use cases about it. So this will be the outline. Just first of all, talking very briefly about emulation, because this is a reverse engineering congress, and I'm assuming most of you know what emulation is about. But anyway, and then we will see a little bit more. So basically, emulation is the process of simulating the execution of code of some architecture into some or different architecture. And yes, this is basically what everyone did some time of playing old games on the PC, and then you go internet and look for an emulator and basically download it, and you can load your ROMs to it. So yeah, this is what we will say emulating the whole architecture to run it. But here we are interested, the reason why we are interested in emulation, in our case in reverse engineering, and specifically in r2, is because it helps us to understand some specific snippets of code, just few instructions that we want to see what are they doing, but maybe not necessarily we want or we can debug it. And also avoiding risks from native code execution. If we are analyzing some kind of malware and we want to see how it works on function or some routine or just a snippet of it, with emulation we can see how it will behave that particular region we are interested in without having to actually executing it. It's also quite useful for helping debugging and for making code analysis. In the analysis that is run on r2, there are some options that incorporate the power of emulation to recover some information. And also we were able to kind of dummy debug non-native executables in some way. So for example, one of the demos I will be showing will be about on top of a P Windows executable that I'm running on Linux. So we will be able to see it anyway, even if we cannot execute it. And let's go straight to the intermediate languages. ESIL. So an intermediate language is a basic utility that it's included in many engines that use some kind of compilation or decompilation. It's basically an abstract machine that helps us analyzing computer programs. You might be familiar with LLVM intermediate representation that some the people from Avast talked about. So we have intermediate languages that are crucial for the process of compilation and also decompilation. And in specific about ESIL, it stands for Evaluable Strings Intermediate Language, and it's a very small set of instructions that we will see a little bit afterwards. And then the syntax for it is based on reverse policy notation. This is basically a stack, and it's designed with demolition and the purpose of evaluation in mind, and not really to be easily and human-friendly reading, unless you're a policy reverser, but that's another thing. And in case of ESIL, we have infinite memory and a set of registers, definition of ESIL. And we have something that is quite cool, in my opinion, which is native register aliases. That means if we are emulating, for example, some x86, we will have the register names are totally arbitrary, but the aliases that Radar2 will give to them will be the familiar register names that we are used to with that architecture. So we will be seeing EAX, EBX, ASP, and so on. For example, if we are emulating ARM, so we will see the usual register name for ARM. So it's not really any functionality, extra functionality, but it's way easier for the analyst to read it, because if he's used to some conventions on registers and so on, it will be way more easy than having random names for registers. And of course, we have the ability to implement custom operations and also calling external functions from it. And why we want ESIL, or why we have ESIL, we need ESIL. First of all, we need some kind of emulation or R2LAN that's set for analysis purposes, and also getting into some particular snippets of code. And when we analyze some functions, it's quite useful. And as well as it's based on strings, it's really easy to generate, to parse, and to modify. There is nothing crazy about it. And it also provides us some extensibility. That means we can define our custom operations for some architectures with ESIL itself. So some custom operations that is not defined by default in ESIL, we can define it using the ESIL primitives. And also, why not? We like to do crazy stuff, so why not? Now I will go for probably the less practical part, but one of the most interesting, in my opinion, that is with understanding what is doing behind what are we seeing, because many people is using ESIL and it's quite easy to use, but if we can understand what's laying behind, everything will make more sense to us. So we have ESIL is basically a stack machine on steroids. I would like to say it like that. And stack machine or push-down automata is that really funny thing. I avoided to put the formal definition that is on Wikipedia. But anyway, you just need to remember that we have an input tape where we get a symbol. We have a current state for the machine. We have as well a stack symbol, and from this we get a state transition that will manipulate the stack, pushing and popping to and from it. And this is the basic idea of a stack machine. And this is a pseudocode of the idea of the parser of ESIL, so it's really easy to understand. We are not, as we said, this ESIL is a strings based, so we will have literally strings with comma separated tokens. So if we are not at the end of the ESIL string, then we will get the next element of the string. We will say the current one. If the current one is an ESIL operation, then we will get the operation and we will perform it. And here I have an indication. The operation that we will perform will might pop previously pushed values on the ESIL stack and used those symbols as operands for the operation. Otherwise, which means this is not an operation, it will just push the current element into the ESIL stack. And here I have a simple visualization. So this is an ESIL expression, a very, very easy ESIL expression. It's just making a sum. We put 3, 5, and the plus symbol. So first of all, we are not at the end of an ESIL string. Remember, we are seeing it here. We are not at the end of this string, and 3 symbol is not an operation, so we push it to stack. Now we are not again at the end of the ESIL string, and 5 symbol is again not an operation, so we push it to stack. Here we are not at the end of ESIL string, but the plus symbol is an operation, so what we will do is pop the values, the previously pushed values to stack, we will pop them, and we'll use them as operands for the plus operation, and we'll perform the operation and get the result. And we can see this actually, should be a demo here. But anyway, I will show you. Yeah, we can see this directly in r2. So we open a shell, you see it okay. With AE, we access the ESIL emulation options, so just 3, 5 plus. I will get it. Okay, it's just emulating the ESIL string we provided. I think I had this maybe a little bit afterwards. So what's the point now? We are basically, I'm not really a computer theorist, but just for the more experienced people with that, we are just here in machine theory. So we have a pushdown automaton right now, and we want to approach a Turing machine. I ripped this, not exactly this image, but this idea from Conrad that's laying there, which gave a really good talk past year. So we want to push down the pushdown automaton to reach as much as we can a Turing machine. And the way to do this is with asteroids, which is basically cheating. And by cheating, I mean adding random access operations and adding control flow operations to ESIL. And those are basically the asteroids part 1. And the asteroids part 2 is adding register access. So we want to have register access. And for that, we will as well add an extra tape. If you remember this image here, we have the tapes. So we will add an extra tape that we will serve as virtual memory. It will be the virtual machine, the ESIL virtual machine stack. So we will be able to use it as virtual memory for the virtual machine. Okay, so basic practical usage when we are inside a r2 shell. All the ESIL options are under the AE subcommand, which means basically analysis ESIL. The most important are the IM, we will init or init memory. The init will just initialize the virtual machine, the ESIL, and the IM will initialize the memory. The virtual machine is included with if we initialize memory, we are already initializing the virtual machine, so we don't need to do I and IM. It's redundant. We can see inside the instruction pointer with IP, we can step until, step over, step skip, registers, and basically this mostly the same subcommands we have with the D command for debugging. We will be able to use them literally the same way with ESIL. Just take into account that we are emulating some snippet of code, we are not debugging, but for stepping and seeing registers and all of that, it works basically the same as with debugging. Okay. And which are the ESIL operands? I was tempted to include here a huge table of operands, but the easiest way is just to check it on Radar with AE and double question mark. And the double question mark is basically because with one question mark, we'll get the usual help of the inline help of the r2 shell with everything we can do from ESIL. You can read those. This is like the full version of everything we can do. I just put the basic ones to start playing with it. And with the double question mark, we will get all the operands. And also some examples under the description. So You can see them here. Okay. There is some important thing to notice, that is the ESIL internal variables, which basically are flags and are prefixed with the $sign. The point with the internal vars is that they are updated on each operation, so they are actually used to set the flags for a particular architecture, as not all architectures update the flags the same way. So we use the ESIL internal flags to take care of that in case of different architectures. So we can check that as well. And I will go straight to the demos. As I showed you before, we have, okay, the AE to emulate. And for example, we can see the registers. There are all 0. Okay, this will show the registers. And if we do, for example, 1, this will basically set the RAX register to 1. It's just pushing 1 to stack, pushing RAX to stack. Then this is an operand, so it will pop the previously values and it will assign the 1 to the RAX register. We can work with that. So I will go straight to show you a couple use cases, interesting use cases and examples, so you can get into it as soon as possible. And that will be it. Okay, where I have it. I will be using one of the famous Yoli correctness by Prof that should be around here. Grab me too, I guess. Yep. So we analyze everything, and let's print the disassembly of the main function. Maybe a little, you see it? Okay, yeah, okay. So what we are interested, yeah, maybe it will be really awesome if you see the crack me before. It's just a very simple crack me that is asking for a password, and you provide a password and it's invalid. So, yeah. Come on. Again, we analyze everything. We print the disassembly of the function, the current sig at main flag, which will give us this. And as we can see here, the interesting part, let's see, okay. We are just interested in this part because we have here a call to scanf. We have some prints, and you can see here the password string, which is the printed string that asks us for the password, and here we have an scanf. That is when we will provide the data through the keyboard, and afterwards it will do some things, some operations, moving around, some sums, some multiplications, and then it will make some comparison, and then he observed this jump. If this jump is not equal, if the comparison between AX and the variable, this variable that is in here, EBP minus zip. So it will jump to the invalid password, otherwise we will win, and we will throw us the password. Okay, you see it here. I have a really bad angle from here to see the screen. Okay, so what we are interested is in the value that will be stored in this variable at the end of those operations. So when the scanf, when we have the call to scanf, then there will be performed some operations, and they will be comparing the scanf, the values to the value, the variable, and the scanf. So if it matches, that will mean that it's the correct password. And the way to do this is, well, one way, get a piece of paper and just compute that. It's just making nothing really crazy, loading two values into, it's getting this value into this memory region, then this other one, I'm seeing really bad. Okay, and then it's moving some stuff around, some multiplications, and that will be it. It's a good exercise for a piece of paper and pencil, but we are lazy, and if we don't want to debug it or anything, we can just get this little snippet of code just after the scanf and just before the jump, and see what's going on in there, emulating those instructions. So I will show you that. We will seek just here. Okay, and then I will initialize the analysis ESIL. Maybe you see it here. Do you see well? Below. Okay. We initialize the virtual machine memory as well, and then just I will show you the state of the registers. As we initialize the virtual machine memory, then we get initialized the stack pointer and the base pointer, but you see that stack frame is not created yet, so they point to the same address. Also, by default, the instruction pointer will point to the address we are seeking. So otherwise, we will have to specify the instruction pointer with IP. And those are the registers that we have modified right now. So I will basically show you again the instruction, the function. Sorry. So we will emulate until just before the jump. We are interested, remember, we are interested in the value on this variable. So we set up the virtual machine and the instruction, we set up the virtual machine and put the instruction pointer just here after the scanf, and we will emulate what is going on until just before the jump. So to do that, we can use a SU, which is basically the step until, and just before. Okay, and if everything went okay, and we can print the values of the variables in this function with this comma, which is analysis function variables display. And if we are just interested in the var.ch, just input the name. We will get it. The command to execute it, to get it with r2, and with the pointers of prefix, we will get it. So basically, this value, which is the same as this one, I was just displaying in two ways. This is the password, I would say, that we are interested, which was stored after making those computations into the variable that will be checked against the input. So now, basically, if we try it, it should work. 338 724, and that's it. Password okay. Okay, I have another demo for you. Yeah, this one was here. Yeah, as I said, thanks to Pov and Julian. I guess it's over there as well. He has some awesome write-ups on those CrackMes if you want to check it out. And as well, I found another interesting demo by a guy that I don't know if he's here, Super Ponybolt, but say hi if you're around. I just picked this up because it's really illustrative and it's not dealing with real malware, so be safe to play with it. And it's just an example on some example files from the resources of a reversing book. I guess it's a book by Secrets of Reversing by Elam. And there is an example to reverse. A defender. Okay, let's see. I will show it you. Okay, let's load it into R2. First of all, note that this is P32 Windows. Okay, I'm running this, analyzing it on Linux. Then we'll analyze it. Let's just list the functions. And if I did some homework and I'd seen that there is just after this function, there is some obfuscated code, and it looks like this function is basically deobfuscating the code that just goes afterwards it. So we will go to this function. 004031. Oops. Okay, here you have the function. It's quite long, but it's basically a decryption routine. And if we print the disassembly just after this triad, that familiar triad, which is a push, pop, and jump PBX, pop PBX, jump PBX, that is push afterwards, before, sorry. So if we just print the disassembly, for example, 25 lines at this offset, we'll see what goes afterwards, and this is basically obfuscated code. This makes no sense. We have even some invalid instructions in here. So what we are interested now, remember we're in this function that we found, is, as we have found that this function is modifying the instruction afterwards, we will emulate the function, just this function, and then we will be able to see the obfuscated code below it. So first of all, I will need to enable the EO cache because I'm going to modify the live. So if I want the code to be able to modify the file itself, so without writing to memory, I will need to enable it. Now let's initialize the virtual machine. And remember that we are seeked, just the seek we have is just at the very beginning of the function. We just seek to the beginning of the function, and we will step until the end of the function. Yep, will take a couple seconds. Yeah, and now if we see that just as it was stepping, the seek changed and we reached the end of the function. Now we make this, we print the disassembly of 25 lines, which will be starting just here as before. We'll see the code that goes right below, and we'll see that now this is deobfuscated. So compare this code to the code that we have before, that was this one. Okay, and that will be the demo. I have just a tip for you in case you're doing something like that. You can basically, cool thing about R2 is that you can load some comments before, just at the very beginning of the initialization of the session. So the easiest way is just getting a text file and putting one command afterwards, line by line. So I will show you just this. This is what we did. We are make the analysis, run the analysis, seek to the function, enable the EO cache. We initialize the virtual machine with this stack. We set the instruction pointer to the offset we are seeked, and we step until the end of the function. That is basically what we just did, and we can basically run it as an initialization script for Radar2. And what it will do is, just after starting it will spawn the shell and run those commands one by one, and then getting you to the session. And this is quite useful because that way you just end up with a Radar2 session with the obfuscated code. So you make the commands to deobfuscate the code, you put it in a file, and then you load the file as initialization. So whenever you want to work with that file again, you will have the code deobfuscated. And that's quite useful for any kind of obfuscated code that's typically found in malware and other places. And that will be about it. I would like to publicly thanks to those people. And I'm really happy that all of them are here because usually they are not where I am presenting. So thanks to Pancake, to Xvilka, Condors, and Squatter that are always like, I'm always throwing spam to them, asking questions, and they are really, really supportive and not really sending me to leave me alone. So really thanks to you. I learned a lot, and all of ESIL I know it's, or rather is probably thanks to them. And so an applause for them, please. And that will be it. Thank you very much. I hope you learned something. And if you have any question, I don't know if we have that much time because we are running a little bit out, but I will be around here the whole day. I'm sure you have seen me before managing stuff. So anyway, thank you very much.